In this video, we're going to review a fundamental tool used in a static analysis, and that tool is called the free body diagram. And what the free body diagram is that it is a highly simplified diagram of a complex structure, and we'll use this person performing a knee extension exercise, and that diagram will be free from all external contacts, and that's going to enable us to represent what are called all external forces drawn on the free body diagram, and that free body diagram will represent the system of interest, and we're going to draw those forces with vectors. So in our example here we have a patient performing a knee extension exercise where an elastic tube tied to the table is providing an extra degree of resistance while this person holds the leg in this fully extended position by contracting the quadriceps muscles. Now, in terms of conducting a static analysis, we're not concerned with the patient's left leg or any other part of the body, but we want to zero in on just the system of interest, and that system is the lower leg, the foot, that has the rubber tube attached to it. But as indicated on the previous video, this is too complex of a structure to analyze directly, so we simplify this complex structure with a much simpler drawing here, and this is our model that we'll now use as the free body diagram. And so the objective here is to calculate all the external forces and the moments of force that are acting on this system that we're using as a model to represent a more complicated system. And so that's what we're going to do here. Here with the free body diagram, just to review once again, we have our simplified diagram of a complex system. We don't have any other contacts drawn into this, so we have the knee, the lower leg, and the foot represented by this triangle. And then we will start adding in vectors to represent the forces coming from outside of this system that are influencing the position of this system. Now, another important element that we always have to add when we draw a free body diagram is our frame of reference. And so we always draw this just off to the side here. The horizontal is our x-axis, the vertical is our y-axis, positive to the right, positive up, and any rotations are considered to be positive if forces that cause rotations going counterclockwise are positive. So I'm going to go ahead and start adding in vectors, and the first vector we always add in is the weight of the system of interest. Now we know that every single element of the lower leg and foot has a weight, but we draw this at what's called the center of mass, and we always draw this representation of the weight of the system downward, perfectly vertical and going down. We also saw in the previous slide that there was an elastic band attached to the distal part of the person's lower leg at around the foot. So I'm just going to represent the point of application of the elastic tube just at the ankle here, and I'm going to draw it along the line of that tube. We know that to do this, the quadriceps femoris muscle must exert a force to keep the leg in the fully extended position. So I'm going to draw a vector with the point of application where the muscle inserts onto the tibial tuberosity on the proximal tibia, and I draw that vector through the tissue through which the force is being transmitted to the tibia, and that occurs through the patellar tendon. And because the lower leg is stationary, despite the fact that there's a force of gravity, there's an elastic tube that's trying to flex the knee, and then there's the knee extensor muscle group that's counteracting the effects of gravity and the elastic tube, the leg doesn't move, and that's because we have an external reaction force that's drawn in, that's attempting to push the lower leg and foot. Really, this is a preventative force preventing the translation of the leg towards the left. So to summarize the static analysis, we'll work many examples in this series of videos. We begin by drawing the free body diagram, and although we haven't done it here, we will label all forces. We have to draw our coordinate system, and we did that already up here on the right hand side, and without a coordinate system we would not be able to interpret the directions of these vectors. We then apply Newton's second law and complete what are called equations of equilibrium, and the base equation of that in the previous video was that the sum of the forces acting on the system equals 0. We say 0 because the system is not accelerating. Likewise, the equations of equilibrium will include the sum of the moments of force, which will equal 0 as well. And then we would solve for all the unknown forces and directions. And so to illustrate the application of the static analysis approach, we're going to look at this box here sitting on a surface. So what we have here is a static condition, and we have a box sitting on a surface, and we want to make sure that we account for all the forces that are acting on an object, and when we add up all of those forces will equal to 0. In other words, all the forces will balance each other if this object is in a state of rest. As you can see up here in the top right hand corner, I have my standard XY coordinate system with directions to the right, upward, counterclockwise rotations indicated as positive. Now typically we would not draw the external surface that the box is sitting on, but I like to draw this in a very light manner or with a dotted type of diagram here, just to provide some context over which that box, with the external surface over which that box is acting upon. The first force that I'm going to draw is the weight of the box. Now typically we would draw this with the point of application at the center of mass and pointing downward, but because these vectors sit on an infinite line of action, I can slide that vector along that line just so I can make sure that when I draw in all my vectors it doesn't produce a cluttered diagram, and you'll see why in a moment. So this is going to act through the center of mass of this object. Now, because the box is sitting on a surface here, this surface will generate what's called a reaction force. A force that's directed perpendicular to a surface is often just generally referred to as the normal force. Here, because this box is sitting on the ground, I'm going to give it the label F for force, GRF, which stands for the ground reaction force, and the magnitude of this force will be opposite to that of the weight vector in terms of its direction, but it will be the same magnitude. Now I'm going to add in another force on the left hand side, and I'm going to call this F push. So if we have a scenario where somebody is pushing on this box, we would represent that force applied at this point. Once again here, we could draw the vector where the point of application is right at the contact point, but that would produce a really cluttered diagram. So I'm just going to put it out here outside the box to indicate that there's a push coming this way, and it has the same effect. Now I'm going to attach another force here, but this force is going to be a pull type of force, and you notice that this force is neither parallel to X nor parallel to Y, but it's at some given angle. And as outlined in the previous video, what I need to do here is I need to decompose this vector into components that are parallel to X and parallel to Y, and to do that we just simply draw a rectangle or a square. In this case, this happens to be a perfect square. And this vector will have a component along the x-axis and a component along the y-axis. And that is then how we would move forward with our static analysis. Now, the box right now does not move vertically because these reaction forces balance. The box is not moving horizontally despite the fact that we have a push force and a pull force. And that's because we have what's called a friction force. And this is the force of contact between the box and the ground that's parallel to the ground. And so what the friction force does is it opposes the push and pull force, and it prevents the box from sliding along the ground. And because this is a static situation, and we then use our first equation of equilibrium, where we add up all the forces in the x direction, and those forces will equal to 0. So in a given problem or in a scenario, you would have to know if this box is moving or not. And so in this scenario, the box is clearly not moving. If it's not moving, the acceleration value on the right-hand side of this equation drops to 0, and then we can just find all of our forces that are directed only in the x direction. Likewise, we take Newton's second law and we apply it in the y direction. And so the same idea applies here, where vertical accelerations are 0. And because those are 0, then we would just simply find all of the y-directed forces, add all of those forces up, and those forces will equal to 0, and that will enable us to find and solve for any of the unknown forces. So this ends our second part of our statics part 1 unit.